Make a decision tree classifier in minutes. By the end, you will have a tiny decision tree that makes real predictions. You will see its accuracy on a reproducible train test split. You will search for a best depth, compare impurity criteria, and inspect a confusion matrix to understand errors. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. Decision trees solve classification problems where you want clear, interpretable decisions. You reach for them when you want a model that you can explain to a teammate or stakeholder. They work well on small to medium data and on tabular features like age, score, or binary flags. The trade-off is that they can overfit when allowed to grow deep, and they usually do not match the raw accuracy of large ensembles like random forest or gradient boosting without tuning. Imagine we have a tiny table of features and a label that says Class A or Class B. The tree will ask simple questions about one feature at a time. Each question splits the data until the leaves decide a label. That is the intuitive idea, a flowchart learned from examples. Strengths are interpretability and fast prediction. Weaknesses are sensitivity to noisy splits and to a limit in representing very complex boundaries. We will build the whole pipeline step by step and see outputs you can reproduce. First, we train a tiny tree and get 2 sample predictions. Now, we train a tiny decision tree and predict 2 labels. This snippet trains a tiny decision tree on a handful of examples and then predicts 2 labels for held-out samples. This example uses the DecisionTreeClassifier from scikit-learn, which learns a flowchart of yes or no tests on features. It fits the model to the training rows and calls predict to produce labels for the new rows. The snippet shows how a shallow tree behaves, and it makes it clear when a decision boundary is simple. If you change the tree depth to be larger, the model can fit more detail and may overfit the tiny data. Next, we split data and measure accuracy in a reproducible way. This snippet evaluates accuracy using a reproducible train test split, where train test split is the utility that splits data into a training set and a testing set so you can measure generalization. This example fixes the random seed so the split is repeatable, then fits the decision tree classifier on the train side and computes accuracy on the test side. The accuracy score is the fraction of correct predictions. If you change the test size, you'll see accuracy vary. And a smaller test set gives noisier estimates, while a larger test set uses more data for measurement and less for fitting. Next, we search over tree depths to pick the best setting. This snippet searches a range of maximum depths and selects the best performing setting on the test split. The code trains a separate tree for each candidate depth and records its test accuracy, so you can spot the sweet spot between underfitting and overfitting. This example shows the practical effect of the max depth parameter. Lower values may underfit and give low accuracy, while higher values may memorize training quirks and hurt test accuracy. You can change the range of depths to explore finer control or to protect against extremely deep trees. Next, we compare 2 impurity criteria and show how they differ in practice. This snippet compares impurity criteria, typically Gini impurity and entropy, and reports their accuracies on the same data split. Impurity criteria are the rules a tree uses to pick the best split at each node, and different rules can yield slightly different trees. The example fits 2 trees that are identical except for their impurity measure, and then prints test accuracies for each. In many real datasets, the differences are small, but on some datasets, one criterion may produce simpler splits or slightly better generalization. Trying both is low cost and often useful. Finally, we inspect the confusion matrix for the chosen tree to see what mistakes it makes. This snippet reports a confusion matrix for the chosen tree, where confusion matrix is the table that counts true labels against predicted labels so you can see which classes are mixed up. The code fits the selected tree and then computes and prints the matrix for the test set. This gives more actionable insight than a single accuracy number because it shows false positives and false negatives for each class. If you see systematic errors, you might rebalance classes, add features, or adjust class weights to guide the tree toward the right trade-off. Recap: a decision tree is an interpretable flowchart-style classifier, great for small to medium tabular data. Use it when you need explainability or a fast baseline, and when features have clear thresholds. Caveat: trees can overfit if they are too deep and may need tuning or pruning. Next step: tune the maximum depth and minimum samples per leaf with cross-validation to find a robust setting before you scale up. If AI Foundations in Python help you, subscribe and watch the AI Foundations videos.